Hello and welcome to Lecture 75 of my class from Data to Decisions. I'm Chris Mack, your instructor. This is lecture part 2 of our series of lectures on Bayesian regression. Now, we talked a little bit about how to interpret Bayes' theorem from the perspective of regression. And we said that the normal maximum likelihood estimation approach looks at the likelihood function. That is, what is the probability of getting this specific data set, y, the vector of all the y values, given a set of parameter values for our model? Okay? Everything assumes we have the right model, but given that, how are these parameters? What parameters maximize this likelihood function? That's what maximum likelihood estimation is. Of course, ordinary least squares is related to that. But in the Bayesian regression approach, we flip things around and we ask, given a set of data, what's the probability distribution for the parameters in our model? To make this conversion, we need to know the prior distribution and the normalizing constant. So we already know how to calculate the likelihood function. This is what we do every single time we do ordinary least squares regression or maximum likelihood estimation for our regressions. It does require us to make assumptions about the probability distribution function for y. For example, ordinary least squares assumes a normal distribution where every y is independent and identically distributed with a constant variance. Of course, we don't have to make that assumption, but we have to make some kind of an assumption about the PDF of y. But we already know how to do that. That's what we've talked about throughout this semester. Then we have this normalizing constant, the probability of getting this data set all by itself. This is independent of whatever the values of the parameters might be. It's used to normalize the posterior PDF, but quite frankly, most of the time we don't even need to do that. If we're going to talk about how we analyze or summarize the posterior distribution in a little bit, and we'll find that most of the time we don't even care about this normalizing constant, so we end up ignoring it. Real new thing, the new thing we're adding in Bayesian regression as compared to maximum likelihood estimation, is the prior distribution. What is our understanding of what the model parameters are and what the variance of y, or the variance of our error term, is before we begin the experiment? So independent of the data, what do we think, what do we believe about this prior distribution? And then finally, we calculate a posterior distribution from that. And the question you might have been thinking about is, how do we interpret this posterior distribution? So the output of a Bayesian regression is not a set of best fit parameters like we do with our maximum likelihood estimation. Instead, it as an output a probability distribution for each of the parameters and a probability distribution, this variance or standard deviation of the error term. We call this output probability distribution the posterior distribution, and it then becomes our goal to interpret this posterior distribution in some way that makes sense for our problem. And usually that involves summarizing the distribution. Like many cases where we collect a bunch of data and we look at a distribution in some way, we often simply report a couple of summary parameters for that distribution of data. For example, a parameter of location or central tendency and a parameter of spread or scale. So we can use the mode, the mean, the median, midpoint of the range, etc. All of these are some kind of a measure of location or central tendency, and it's one of these location parameters that will be our quote-unquote best estimate of the parameter value. Mode, I think, is the most popular because it seems to interpret the same way as a maximum likelihood kind of estimation for the posterior. We also need to have some kind of a measure of spread. This becomes some kind of a measure of how uncertain or how certain is our knowledge or belief about this parameter now that we've done the experiment. We use it to create what are going to be called credible intervals, or quantiles of that parameter. We'll talk about that. Excuse me. We'll talk about that in a little bit. So what does this posterior distribution say? Well, it describes how much data has changed our beliefs, right? So we have a prior belief described by the prior distribution. Then we have this data, and the data will be shifting our belief in some way, or maybe it won't. It might turn out that it completely confirms our prior beliefs. But that's basically what Bayesian regression is doing, is giving us a mathematical way to describe how the new data shifts our prior beliefs. And there's an interesting and important theorem called the Bernstein-von Mises theorem that basically says if we have a big enough set of data, prior distribution doesn't matter. Unless we have some special priors like zeros or ones where it kind of forces certain behavior in our posterior independent of the data set. Other than those extreme cases, if I have a really large data set, then the prior doesn't really make much difference. The data is so convincing, it has so much information about what's really going on that it will shift our belief system to be governed only by the data. In other words, if we let the number of data points go towards infinity, the posterior distribution will approach normal distribution with a mean equal to the maximum likelihood estimate. This is basically a restatement of the central limit theorem, and it basically says the posterior distribution becomes the same as the likelihood function. And the effect of the prior is large when I have a small amount of data, but the more data I collect, the impact of the prior gets less and less and less. That makes sense intuitively, but it's also an outcome of the mathematics of Bayes' theorem as well. The prior distribution is the key, right? Figuring out how to summarize our current information or knowledge in terms of a prior distribution for the parameters. What we really, when we talk about the prior as a function of this parameter set, that's the betas as well as the standard deviation of the error term. This is shorthand notation for prior of these versus given all the information we have about the problem before we start collecting data. Sometimes we have no information. We're going to talk about that in a moment, in which case we say we have an uninformative prior or an objective prior, and it usually is modeled as being some kind of a flat distribution. But almost always we have some information, just a matter of how do we grab it and put it into this format. So the prior choice is the key to successful Bayesian regression. Non-informative or uninformative prior, sometimes called a baseline prior or an objective prior. This is the case where basically assume some kind of a uniform probability over some range of values. And then we say, I don't know whether it's this value or that value. They're all equally probable to me. So that implies a uniform probability. But uniform in what sense? You can imagine lots of flat priors. All right, so suppose we have a linear regression with a straight line. Our model is a straight line. Well, we can say the slope has a uniform prior distribution over some range of slopes, maybe even all slopes from minus infinity to infinity. But I could also think about an angle of the line. Say, well, there's a uniform distribution of angles, minus 90 to plus 90. Why not use a uniform distribution of angles? Why not use a uniform distribution of the sine of the angle of that line? All of these are uninformative in some sense, in that I'm saying they're all equally likely, but equally likely angles are not the same as equally likely slopes. So exactly what you mean by non-informative can sometimes be not very intuitive. But more important prior is the substantive prior. This is where we have some problem-specific information that came prior to our experiment, and we capture that based on previous data, previous experiments, previous knowledge, and we put that into a prior distribution. Sometimes we assume that our understanding of the betas, the parameters of the model, is completely independent of our estimates or guesses about the error term in this experiment. So we'll assume that they're independent and just multiply the two probabilities like this. Sometimes some kind of a joint probability distribution will be required. That is, the uncertainty in the y values might be a function of the values of the parameters themselves. And finally, if we were to pick a special prior, like a delta function, this is 0 everywhere except for at a specific point, then that's going to fix the parameter independent of the data. So if I pick the prior to have such a narrow distribution, then no matter what the data says, I will always have a posterior that's fixed by the prior. Now, if we're doing that, why bother even performing the analysis of the regression? It just says, I'm so convinced about my prior belief that I ignore all new data. It's not very scientific. All right, so you're going to choose non-informative or substantive. Well, I'm going to say something that I think some Bayesians are definitely going to disagree with me. I talked a little bit about this almost religious character to the frequentist versus Bayesian interpretations of statistics. And for true committed Bayesians, there should be no reason to ever do anything other than Bayesian regression. And if you don't know anything, use a non-informative prior. I don't buy that. My perspective is, if you don't have any prior knowledge help you, why even bother with a Bayesian regression? That's the whole point, is to incorporate your prior beliefs and use the regression to transform your prior beliefs into beliefs based on the data. If you don't have a substantive prior, I say I bother with Bayesian regression. As I said, Bayesians will disagree with me, and they'll be constantly advising you to use a non-informative prior and do a Bayesian regression anyways. I don't think so. Use maximum likelihood estimation unless you have substantive, informative priors that you can use. And I think most of the time you do. Not always, but most of the time. It's just a matter of actually collecting them. Sometimes you might have to reparameterize your model to make use of the priors. Let me give you an example. Suppose I have a linear regression with a straight line, right? The simplest model you can imagine. Maybe I'm trying to model the viscosity of water as some function of temperature. So xi is a function of the temperature, and I want to model the viscosity. What's the meaning of beta 0 then? Right? If xi is the temperature, well, beta 0 would be the value of the model at a temperature of 0. Well, in this example, a temperature of 0 is not useful because what's the viscosity of water, liquid water, at 0 degrees Kelvin? It's not physically meaningful. It doesn't do anything. So how could I possibly come up with a prior for a non-physically meaningful value for this parameter? Well, if we reparameterize our model, we can get away from that. What do? Well, the easiest way is to shift the axis by x bar being the mean of the data, all the x values I'm using in my experiment. This does nothing to the slope, but it changes the value of beta 0, the intercept. So I'll end up with a new intercept. Now, what's the interpretation of the new intercept? It's the value of my model, and xi equals x bar, which is a physically meaningful value. And now I can supply prior for what my prior knowledge of the viscosity at this particular temperature for liquid water really is. It makes the interpretation and the use of Bayes' theorem and Bayesian regression much more useful. Further, by picking x bar as the amount that I shift, it essentially makes the prior of the intercept independent of the slope and its prior, which is also quite useful. Let me give you another prior choice example. This is popular in some kinds of work that you might do. Again, let's consider a linear regression, and let us set our prior to favor a null hypothesis. This is kind of like how we do hypothesis testing with with Bayesian regression. I will assume that the slope is 0. But assuming it's 0 is kind of our null hypothesis really means I'll have a probability distribution for the slope with 0 mean. Right? I'll still have some kind of a variance or standard deviation slope, and I'll simply make it large enough to allow for the expected range of possible slopes. Picking that is going to be the most important or the hardest thing to kind of get your head around. But nonetheless, we're essentially saying my null hypothesis, my prior belief, is that there's no relationship between y and x. Now, does the data contain enough information to push me away from that prior belief? If it does, then I'll have a new estimate for the slope, and I'll essentially, falsify this null hypothesis. Another popular example of using priors is to use conjugate priors. If I have a certain likelihood distribution, right, where I've made assumptions about how the y's are distributed, there are some prior distributions that allow analytical calculations of the posterior distributions. In fact, there's only very few possible prior distributions that allow that. And those special cases are called conjugate priors. And for any given likelihood function, probability distribution, then there will be a specific conjugate prior that will allow an analytical calculation of the posterior. The example that is most commonly used is the IID normal error. So if all the y values have independent and identically distributed Gaussian errors, conjugate prior for all the parameters will be normal, and for the error variance will be gamma. But in general, we're going to solve Bayes equation numerically anyways, whether we're using conjugate priors or not. And the most common way to do this is to use Markov chain Monte Carlo sampling, sometimes Gibbs sampling as our approach. And we basically take our prior distribution and we randomly pull random numbers for the values of the parameters out of these distributions and then calculate the value of the probability in the posterior. Do that 10,000 times, 100,000 times, something like that. So we'll get a set of points that we can then summarize as our posterior distribution. For example, we can calculate the mean, or what's very popular, maximum a posteriori, whatever the right Latin pronunciation of the word is. The maximum a posteriori distribution we call the map estimate of the mode. So everyone just says map because, I don't know, maybe people like me are having trouble pronouncing that Latin. I never took Latin. But we take the map estimate of the mode. That becomes our best estimate of the points of the parameters. Now, what's the relationship Bayesian regression and ordinary? All right, we'll consider a linear model. Here I'm going to consider a multiple linear regression example. And let's assume that our likelihood function is a product of normal probabilities with a constant variance. In other words, I'll assume independent, identically distributed Gaussian errors. Well, that's ordinary least squares regression, right? But now let's do a Bayesian regression, and we need to choose a prior. Let's choose something called the Jeffreys prior, obviously named after Jeffreys, the guy who first came up with it. And it essentially says the probability of the parameter set and our error variance will be proportional to 1 over the error variance. It's uniform. It's also improper. Why is it improper? Well, it's improper because a true PDF must integrate to 1, but the Jeffreys prior integrates to infinity. There's no limit, plus or minus, any of the betas, so possible ranges. That makes it an improper prior and kind of hard to interpret from a Bayesian perspective. Mathematically, we can go through the calculations, and the resulting posterior distribution is p distributed about the maximum likelihood estimate parameter estimates. Maximum likelihood parameter estimates. Well, that's exactly what we get when we do ordinary least squares regression. So with the Jeffreys prior, Bayesian regression becomes identical to ordinary least squares regression, but with a slightly different interpretation. For example, credible intervals versus confidence intervals. We'll talk about that in a moment. So there is a way to relate OLS to Bayesian regression, but only if we have this improper, non-informative prior called the Jeffreys prior. Of course, this makes interpretation of what the prior means almost impossible to think about, since it's not a proper prior. Nonetheless, it's at least a little bit comforting to know that in certain assumptions, the Bayesian regression will produce the exact same result as an ordinary least squares regression. All right, interpreting the posterior, we have two things. We can use the mean, but most likely the map estimate of the mode as our best fit values for the parameters. And we need to put some kind of a range around these best estimates of the parameters. In the frequentist view, we talk about confidence intervals. Our parameter is an unknown constant. We have, if we were to repeat our experiment a large number of times, then 95% of the calculated confidence intervals would include the true value of that parameter for the case of a 95% confidence interval. So that's how we interpret the meaning. For Bayesian regression, we assume that the model parameters are random variables. And the credible interval is the range over which there's a 95% probability that whatever this random variable value happens to be, it falls within that range 95% of the time. So in a certain sense, it's a more, it's an easier interpretation. But I think most of us kind of think confidence interval, credible interval out the same way. All right, what have we learned in Lecture 75? In our coming lectures, we're going to try to get into some more practical details of how to actually perform Bayesian regression. But let's look at what we've learned so far in this lecture. How is the posterior distribution used or summarized to tell us something about model parameters? What does the Bernstein-von Mises theorem tell us about the relationship between the prior distribution and the posterior distribution? What is the difference between uninformative and substantive priors? What is the Jeffreys prior, and how does it apply to linear regression? And finally, explain the difference between confidence intervals and credible intervals. Well, still more to learn about Bayesian regression. Till then.